All right, welcome. In this video, we're going to continue talking about proofs, and we're going to write some more proofs. And we're going to talk about the distinction between formal and informal proofs. We've already had an introduction to both of these ideas, but now we're going to take some time to do a couple more examples of both formal and informal proofs. So I wanted to start with a proof related to sets. So maybe a broader comment here is that the proofs that we're going to write in this series of videos, but in general in mathematics and computer science, can range in their topics and their subject matter quite a lot. The variety is immense, ranging through, say, set theory or logic, the topics that we've been talking about here, into number theory, simple number theory with prime numbers and so on. Other mathematical realms, maybe graph theory is important to computer science. And all of these different theories, we might be able to prove a theorem using the same techniques of logic that we're proving here. Now, what that means is the subject matter could be widely varied, but because we are trying to study the tools, the actual skills of doing logic and reasoning and proofs, we're going to try and keep the subject matter, at least at first here, within that same realm, sets and logic. So the first proof I'm going to tackle here is with sets. After we get comfortable with these techniques, then we'll branch out and start talking more about algorithms and other things of interest to computer scientists. But to start now, I do want to do one proof related to sets. So here are my proof related to sets. Just to give us something to talk about, I'm going to start with two sets here, S and T. And then maybe I'll just jump down here to the theorem, because this is what I actually want to prove. I want to prove that if S is a subset of T, then S is equal to S intersect with T. So if I want to prove this mathematically, it means there's a lot of things I need to bring to bear for this proof. And when I say things I need to bring to bear, I mean different facts, different propositions that are probably going to be relevant to the argument that I want to make. And those propositions that I want to bring, based on some of the definitions that we've been looking at in the last couple of videos, we want to identify, are these premises? What kind of premises are these? Is this an axiom? Is this a hypothesis that we're going to make? Is this some other theorem we've proven before? Are these steps that we're making along the way intermediary conclusions that are going to lead us through a valid argument to the conclusion that we want? The conclusion that we want is this statement here. Now, the other thing I'll maybe highlight in this statement, a couple properties of it that are going to be important when we want to tackle it. It is phrased in this common way, the if, then. A lot of the theorems that we're going to have are going to be phrased in this way. If, then, the first part, the antecedent of this conditional statement, is going to be things that we usually are going to assume to be true, and then the goal is to prove that based on those assumptions we can reach the conclusion. And so that's the strategy we're going to take again here for this direct proof. We'll assume the antecedent and try and argue that the consequent is true. Okay, so in this case, there are a couple other things that we might need as well. We'll notice that this theorem has to do with set theory, so some of the definitions of set theory are probably going to become important for us. Two definitions that I thought were important that I would list here: the definition of a subset and the definition of what it is for two sets to be equal, which, if we recall from an earlier video, was tied to these two subset relationships. Oh, I actually had a typo there in my slide, so I actually corrected that. But our definition of equals is actually going to be when A is a subset of B and B is a subset of A. I had this just the same thing written twice there. So again, this is related to the idea that with the numerical equality, we can prove with if A is less than or equal to B and B is less than or equal to A, then numerically that would mean A is equal to B. Well, when we tie this into sets, we get the same idea where we use the subset equal to instead. Okay. Now, another definition that might have been worth bringing in here, but I'm going to leave unstated at least for the moment, is the definition of what intersection is. But hopefully we can recall from our video on set theory what that definition is. And if not, I will, of course, bring it up as it becomes relevant. Okay, so these are all the different things that might be important for us. We want to prove this if-then. We might need to know the definition of a subset and equals and maybe intersect as well. And then we can argue, hopefully we can try and make this argument. So let's try and start the argument. Remember how we start an argument. We're going to start it with a proof here. And that proof, we're going to start, since this is an if-then, we're arguing we need to assume the antecedent. So we start by assuming S is a subset of T. That S is not a subset of T, there's nothing for us to prove. So we'll start by that assumption. Assume S is a subset of T. Now what this next statement I've got here is an application of the definition. Now remember how I mentioned in the last video how a definition works. We can think of this if and only if as a two-way bridge. If we're on one side, we can go to the other side and vice versa. So we know here that S is a subset of T. That's this definition here, of course, with just different names for the variables. And then here, this is what we can conclude. So here, that's what I'm concluding. So since we know S is a subset of T, it must mean that if X is an element of S, then X is an element of T. Again, just a little relabeling of the variables here, but the property is down here stated exactly the same. Okay, so we can continue then. Again, this is what we know. Now, what is it that we're trying to argue? We're trying to argue that S is equal to S intersect T. So we've got what we can assume. Here's our starting position, and this is where we want to go, that they're equal. Now remember, the equalness, to prove they're equal, we need to show two subset relations. Now I'm going to go ahead and break those two subset relations into their own separate proofs. So the first one I'm going to call a lemma. You can think of this as a subroutine or a subproof inside our proof. We're going to break out the first one, the first lemma, which is going to be that S is a subset of S intersect T. Okay, so this is what I want to prove. S is a subset of S intersect T. And I'm going to again rely on the definition of subset to help me show how to prove that. That is, I need to show that if X is an element of S, then it's in the intersection as well. So for every element, if it's in this set, then it will be in this intersection as well. So let's see if we can do that. Again, that's another if-then statement I'm trying to prove. Okay, so I'm going to assume the beginning. So I'm going to assume, to get us started here, that X is an element of S. So I start off with some element of S, and I'm trying to argue that this element, so looking ahead here, is also in the intersect. Okay, so I'm also trying to argue that it's in the intersect because that's the definition of what subset means. Okay, so let's see if we can follow the steps that I follow. First, we've said by definition here, we're just assuming the antecedent here, that X is in the set S. Okay. Then, what do we know? Well, we've got this statement here. If X is in S, then X is in T. We've assumed X is in S, that's the antecedent. So remember the rule we used last time called modus ponens is going to allow us to conclude then that X must be in T as well. So that's this next conclusion here. Okay. Applying these 2 points, we get X must be in T as well. Now, since X is in S and it's in T, that means it must be in S and T. So that's what I've got here. X is in S and X is in T. We're just putting these together using the rule called conjunction. Then we're going to say, well, this, I don't have it listed here, but maybe we can flip through our notes. This is the definition of S intersect T. X is an element of S intersect T if and only if, by definition, it is an element of S and it's an element of T. So since we know it's in this property, we know that it must be in the intersect. Okay. Then what does that mean? We started with the assumption that X was in S, and now we've concluded that it's in X intersect T. So if X is in S, then it's in S intersect T, that means S is a subset of S intersect T. So here, this last little argument here is once again applying the definition of a subset, but now backwards. We're saying if X is in S, then it must be in the intersect. following the path backwards then that means S must be a subset or equal to S intersect T. Okay, so we got this lemma all in one direction. Okay, this is one direction showing S is a subset of S intersect T. We now need to go the other direction, show that S intersect T is a subset of S. And once we have both of those directions, we get A equals B for free. Okay, so we'll continue. We now want to go the other direction. S intersect T is a subset of S, right? And again, how are we going to do this? Well, the argument structure is going to be the same, in that we're going to start by assuming we're in this set, and then we need to argue we're in this set. So let's see. So assume that X is in S intersect T. Again, we're trying to argue it's in S. Now remember, if X is in S intersect T, by definition of intersection, that means X is in S and X is in T. Now we'll use the conjunctive simplification. Since we know it's in S and we know it's in T, that means it's in S. Okay, so if it's in S intersect T, then it must be in S. Remember here I'm just restating what we've just proven, but then noting that this matches the pattern of my definition up here, I follow it to the other side and conclude that S intersect T must be a subset of S. So we get our second lemma. Now remember, we've got both of these lemmas in the directions that we need to prove them. And so that's this side of the definition of equals. So once again, we follow back over and we can conclude that S must be equal to S intersect T. And that's what we were trying to prove. That was where we were trying to go. So we're done. Okay, now this was the informal version. To formalize this, what we need to do is we need to, again, start selecting sentences, propositions, giving them names, like P and Q and so on, and then using those and our rules of inference to argue the structure of this argument. Are we sure that this is a valid argument? Have we only followed valid rules of inference? The answer is yes, but not unless we can codify that and make sure. So let's see if we can go ahead and do that. So to get us started, I've decided to set ourselves up with the following sets of propositions. This is a little bit more in depth than the last one we did in the last video, so we have more propositions here. So let's take a look. We've got sort of two simple ones to start off. S, I'm going to call X is in S. T is going to be X is in T. I'm going to let B be the proposition X is in S intersect T. So we need that one as well. Then we have a couple other propositions of importance. S is a subset of T. We'll call that one U. S is equal to S intersect T. That's really kind of what we're trying to prove, or a logical combination of those two. And then remember, to prove the equality, we split it into the two subset propositions. So that's what I've got here as well. The E1 and E2 are the two subset propositions that we might need to prove. So let's go ahead and see if we can codify some of the propositions involved in our proof. So the first one we had was our definition of subset. So what it is to be a subset. Out of our statements here, which one sort of matches that form is statement U. A and B here is sort of stated generally. We could plug in any two sets we want, and we're going to use this over and over again. But maybe some of the ones that we were interested in was this one here for S and T. Okay, at least we're going to apply that this one in the first case. Okay, so one way we could codify this, at least for our two sets S and T, is as follows. We've got U is got this form. The S is a subset of T form, so we'll call that U. Then we have the if and only if. That's the definition. It's establishing our relationship. And then we have this right-hand side that says if A is in A, then A is in B. Okay, well, we don't have A's and B's. We have X's and S's and T's. So what did we have here? We had S as a subset of T, meaning that if X is in S, then X is in T. So if S, then T. Okay, so this definition expresses or is expressed by this logical proposition. Okay, so another definition then was our equality. Well, now remember, for two sets to be equal, Which two sets were we trying to show were equal? These two here, so we'll call that one E. To show it was true, well, we had actually split that into our two subset proofs. So if E1 and E2, we need both subset proofs to be true, so I've joined them together with an AND. Okay, so that's this definition, the AND there, of course. And then let's take a look at our proposition, the theorem that we're actually trying to prove here. So this theorem, the way we want to state it here, if S is a subset of T, we called that one U, then S equals S intersect T, and we had called that one E. That's a very simple U implies E structure. Again, this is a conditional, as we had mentioned when we were proving it informally, but now we've explicitly stated, look, this is a U implies E structure. That means it makes it pretty easy for us to see that if we want to prove this, we need to assume U and then somehow get to E. Okay, so not surprising, we're going to start off our proof by assuming U. And the rule we're using this is called hypothesis. We're just assuming the hypothesis so that we can argue our way to the conclusion. Okay, now U, by our definition here, following the bridge to the other side, applying our definition, we're going to get to the S implies T. Now, I've just written that sort of more with English here, so if S then T, but we could have left it symbolized as above there, S implies T. And that was, again, applying definition 3. Now remember, now is where we're going to split into our two lemmas. So let's consider our first lemma, lemma 1. Lemma 1 was this subset proposition, which is just E1 by itself. So I just stated that as E1 by itself. Okay, now E1 by itself, which is this subset relationship, it's got two components to it. We have to show this subset relationship, which means we're going to assume that S is in this set S. Well, that is assume X is an element of S, so that's assume S. So we'll assume that. That's a hypothesis because we're trying to prove this subset relationship. Okay. Then the next statement says, well, then T. Well, how do we get T? Well, remember we had our definition of S implies, S is a subset of T. We've assumed S is a subset of T. That was up above here. And so we got to this point here, if S, then T. Now, since we had S, plugging that in with our modus ponens, remember, that just gives us T. Okay, what was T again? That X must be in T. So we glued them together, S and T, adding them together using the conjunction rule by just taking two true propositions and just ANDing them, gives us S and T. Remember, that is X is in S and X is in T. And that was the definition of intersection. X must be in the intersect. So here again, applying the definition of intersect, we now know we're in B. X must be in the intersect. So what did we do? We assumed S, argue, and got to B. So that means we've just argued if S, then B. Okay, so again, if we start with an assumption, a hypothesis, argue using only valid rules of inference, and we arrive at some other proposition, then we've argued S implies B. Okay, so we've argued this now by the definition of implication or conditional, and so that's all we needed to argue E1. That was the definition of E1. We were trying to prove this subset relationship here. Okay, so we'll try again. Let's keep going. We'll codify now lemma 2. So lemma 2 was E2, right? The other direction. S intersect T is a subset of S. Okay, so that's what we're trying to prove. So now we're going the other direction, so we need to assume this. We need to assume that X is in S intersect T, so that's what we were calling the proposition B. So we'll assume B, again our hypothesis. Then if X is an element of S intersect T, by the definition of intersect, that means now S and T. And that was, again, we've followed that same bridge, the definition of intersect, backwards. Here we went one direction, here we're just going the other direction. We went going from B to S and T. Okay. And now, we didn't actually need both those pieces. Where were we trying to get? We were trying to get to this end, which is x's and s. We only need the s bit. So I'm going to use conjunctive simplification to just break the s off. You know, delete the t. We don't need it anymore, so we just get the s. So that means B implies s. So B implies s, definition of implication. And that was the definition of the subset relation we were trying to prove. So we're done. Conclude E2, what we were trying to prove. Okay, remember E1 and E2 together make E. That's this definition here, so we follow the bridge over here. So E, so we're done. We're trying to prove E, or U implies E. We started with assume U, argue, 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 get to E, therefore we must have proved if U, then E. So started with an assumption of U, ended with a conclusion of E, therefore if U, then E. Okay, close off our proof because we're done. And we've concluded our proof. So this is actually an informal proof, or sorry, we've now formalized our informal proof by taking our proof in natural language, in English, and filling in some of the formalism by showing the symbology, the symbolism that we would use for the propositions, and then also highlighting some of the logical rules of inference that we use as we go. Okay, with all that said, more for just to save myself a little time and to save ourselves a little bit of symbology, I did not include the definition of intersect, which is another one that I could have included here, which would maybe been another line or two, another couple propositions, but well, we mentioned when we used it along the way. So we didn't exactly skip over it, we just didn't include it symbolized here. We could include, say, definition 5 here. So we've now seen a couple formal and informal proofs. So formal proof, we can now sort of define, give it a formal definition, is going to be, a formal proof will be one where we use propositional logic, where we use our valid rules of inference, but where we also signify which rules of inference we're going to be using along the way. We contrast this to an informal proof, where we might skip some steps, usually obvious steps, not ones that would not be obvious. And then we might also, and usually actually, omit formalization in propositional logic. Part of the reason we do that is because formalization in propositional logic becomes very tedious. And usually, as I've mentioned in the last couple of videos, our internal logical computer is typically strong enough that we can observe an informal proof and judge whether it is valid or not without having to see it brought all the way down to symbology. But maybe if we wanted to use a machine to check to see if our argument was valid or not, well, then we would want to put it into symbols. The machine's going to be a lot better at it. So usually, and for the bulk of this course, and for wherever you may encounter mathematical logic and mathematical proofs in the future, you're going to encounter informal proofs, where we might skip steps, where we sort of mix some natural language in with some formal mathematical language. We might skip from, you know, some just verbal description into some algebra and then pop back out, maybe have a diagram and so on. All of this is to make the proof easier to digest by the audience, which is typically another human reader. So both of the proofs that we've encountered so far have been both informally stated and then we formalized them. You'll notice that the way that we've done this is we started with an informal proof and then we've formalized it. It's very rare to try and just write the formal proof raw. Again, formal proofs aren't very useful for anything other than studying and understanding proof structure, and once you get familiar with it, you usually eschew it for just writing informal proofs. With that said, though, I do want to encounter, I do want to take a look at a couple more formal proofs before we push them to the wayside. Okay, but we did a proof on sets, and we're going to continue to stick with sets, but now I'm going to move to sets of numbers, not just any old set. And that's because, well, we really do need some subject matter if we want to keep proving interesting proofs. So sets of numbers tends to be the next interesting thing to start doing proofs on. And it's easy if you're a mathematician to get really bogged down and lost in numbers. Numbers are cool, and if you're a mathematician, you'll find lots of interesting things to prove about numbers. But I anticipate that a lot of us are computer scientists, not necessarily mathematicians first, maybe mathematicians as a hobby or second. But I'm going to try and shift our subject matter to algorithms and computer science as soon as possible. But until we can get there, bear with me as we talk about numbers. And numbers are still kind of interesting, so let's talk about them. So here's an interesting property, one that you may already know of and maybe have even proven before for yourself or have had proven to you before. Say we have even numbers. Remember we defined the even numbers in an earlier video. I'm going to use this double bar E here. And specifically, I'm going to be thinking of even natural numbers, although this could apply to integers as well. But here I've got this proposition, if n and m are both even numbers, then n times m is also an even number. And I think there's more than one way we could prove this, actually. And you might have a couple clever ways in mind. One clever way that pops to my mind is using a binary expansion of the numbers, because detecting even numbers in binary is really easy. Let's just use maybe a more natural number theory way to prove it. So follow with me. Again, we've got this if-then structure in what we're trying to prove. We're proving a conditional, so we need to assume the antecedent, and then we're going to argue, and try and get our way to the conclusion. So we'll start at the beginning. Assume n and m are even. Now it's here where maybe our instinct's starting to kick in. Where do we go from here? We often start with a hypothesis like this, which is our starting ground. But then what else do we have to bring to bear? Well, probably the most useful tools that we have, at least when we start, are the definitions. What definition could we use here? Well, what about the definition of an even number? And there's more than one, but we presented one definition of an even number, which is that it can be written in a specific format. So I'm going to apply that definition to both n and m. So I've done that here. I'm writing, so n is equal to 2k and m is equal to 2l. I've changed from k to l to make sure I'm not reusing a variable. That would be an error in a program, and it's an error in a proof too. And here I'm strictly saying where both k and l are natural numbers, which is again the definition we had for an even natural number. Okay, so applying the definition of what it means to be even, I arrive at these states. Now what do I want to do? Well, now I want to know what n times m is, and here hopefully I'm going to rely on the fact that we've done a lot of algebra, so your algebra skills are probably pretty strong. So you'll notice, well, if I take n times m, what does that mean? That's going to be 2k times 2l, and a little bit of shuffling around of brackets and numbers, that gets us 2 times 2kl. And we'll notice that this is of this same form, 2 times a natural number. Okay, so since n times n can be written in this form by the definition of even, it must be even as well. And that's what we were trying to argue. Now, there's a few steps I maybe skipped here. Not trying to skip too many, but if we fill in every single step, we tend to get down to some real nitty-gritty, and we don't necessarily need to spend a lot of time on that. I will mention a little bit here. This proof, we're now done. This proof establishes an interesting property about the even numbers, which is what, well, maybe I'll introduce it here. This is called the closure of the even numbers under the operation multiplication. Closure means if you take two numbers and you apply the operation, in this case multiply, and you arrive back in the same set, then we've shown the closure of that set. A set is not closed if you can find two numbers and say you multiply them together and you get a number outside that set. So maybe we'll see that in a bit. It's important, though, that I've sort of mentioned in this comment here that we've relied on a few other properties in our math knowledge or math understanding that we're taking for granted a little bit here, or at least leaving unstated. Well, we didn't say what the definition of E is, but I brought that up. The associative and commutative laws of arithmetic, well, that's where we're shuffling around some of our brackets here and maybe moving the 2 to the other side of the k and so on. These are our commutative and our associative and commutative laws in arithmetic. And then we're also assuming that 2 times k times L is a natural number, as long as we already know that k and L and 2 are natural numbers. And this is the closure of natural numbers under multiplication. That is, if I have a natural number and I multiply it by a natural number, do I get another natural number? And the answer to that is yes, but we're taking that without proof here. Okay, we're assuming that is true without proof. And hopefully we don't have to prove some of these very simple properties of natural numbers, although if someone's a true skeptic, we might be able to prove it to you as well. Okay, let's consider a formalization of this. Again, I'm going to have to leave out a little bit here. This isn't a complete formalization because we're leaving out associative property, we're leaving out the commutative property, we're leaving out some of the definitions. But here's some of the propositions that I wanted to include. So n is in E, n is an even number. M is in E, M is an even number. These are two propositions here. And even though I've stated this in sort of one form, this really is two propositions. This is n is in E, n is even, and M is even. Okay, and M is in E. Okay, I've got this one down here as well. All right, and then here are some of the intermediary propositions that we had to argue as well. Okay, some of the intermediary ones, I've given them names as well. So let's follow through the proof again. Let's see if we can codify this up. So I mentioned this was an and here. So we called these two propositions P and Q. So if P and Q, then U. That's where we're trying to get the last proposition. Okay. Then how does our proof go? So we start by our hypothesis. We're going to assume the antecedent, the P and Q. So we'll assume the P and Q bit. All right, now where do we want to go with that? Well, remember, when you have a conjunction, an and, usually what we want to do is split it up. So we've actually gone 2 steps here. And so I've indicated that here. Again, sometimes it's tedious to write down every step. The first step was we split P and Q into P and Q, separated. Then we applied the two definitions of even that we have. P implies R, so let's follow through that. P, which is saying n is even, implies that n is equal to 2k. And then same thing with Q. Q saying that m is even implies S, that m is equal to 2l. So here, using simplification and 2 applications of the definition, we arrive at R and S. Now, we get to T by doing algebra. Okay, we get to T, this bit here, by doing our algebra. So that's where we relied on associative, commutative, and the closure of natural numbers. But once we've got to T, that's the definition of even, we can apply again and get to U. So we're done. Okay. So again, formalizing this by trying to encode it into propositions and symbols, and then trying to identify the rules of logic that we use, the rules of inference that we use on each step. Okay. All right, I think I have one more proof I want to do, which is, can we do the same thing for odd numbers? Are odd numbers also closed under multiplication? Okay, and the answer is yes, because I'm asking you to prove it, or us to prove it here. So can we go ahead and prove that? And then I'm going to maybe leave as an exercise, what about other operations like addition, subtraction, division, and so on? Are the sets of even and odd numbers closed under those other operations? I'll leave that for you as an exercise to think about and maybe prove if you want to. But let's start with this one. So this is closure of the odd numbers under multiplication. So if you have an odd number n and an odd number m and you multiply them together, you get an odd number 2. Let's go ahead and prove. And remember, We've seen a couple of these proofs now, so we need to start with our hypothesis, assuming the antecedent. So we'll assume n and m are in O, n and m are odd numbers. We're trying to argue to the conclusion that the product is also odd. So what do we know about them? Well, what's the definition of an odd number? Well, the odd number wasn't the 2k, it was the 2k plus 1. Okay, the remainder of 1, right? And 2l plus 1 for m then. Okay, same conclusion, k and l must be natural numbers. Okay, now I'll multiply them together, and again, this one's going to rely a little bit more algebra, but let's see. We take our two numbers, I multiply them out. Okay, if you need to double check my math here, go ahead. But you'll notice what I'm doing is I'm going to take these first three terms. We can see each one has a factor of 2 in it, right? So I'll factor out the 2 of each of those terms. And I'm left with this inner term, 2kl plus k plus l. Now, assuming k and l are natural numbers, then this whole thing is a natural number. So that means I've now written this in the form of an odd number. So we can say, yeah, this is an odd number, so n and m must be odd. And we're done. Okay, so again, using the same idea as before, this is the closure of the odd numbers under multiplication. So two odd numbers multiplied together is always an odd number. Two even numbers multiplied together is always an even number. Again, think about that for addition, subtraction, and division if you like. But let's finish off by formalizing our proof. So once again, we're just going to try and split this into different propositions, give them names. So probably following the same pattern that we just saw in our last proof. We've got n is odd and m is odd as two propositions, and then the product nm is odd is our other proposition. So that was p, q, and u, so we still got p and q implies u. And then our interior propositions like r here, which is, this is just applying the definition of n is odd, and then m is odd, right? So again, setting up our proof here, we'll assume our p and q. And then what did we do? We did simplification and then applying the definition of odd to get to r and s. This is our expression of what the odd number looks like. Then we do our algebra. Then we multiply them together to get to t. And remember, that's going to rely on some algebra stuff. Here, why are we leaving these steps out? Well, one of the reasons I'm leaving these steps out is this video and this video series is not about algebra. Hopefully, your grade school math instructor argued that these rules of algebra were true and helped to show you that they were true at an earlier point. So instead of trying to, what we call, go down to base principles, go all the way down to the bedrock and try and prove everything from there on up, we have to stop somewhere. We have to cut off somewhere. So here I'm saying, I hope you trust me that natural numbers are or multiplication and addition are associative, commutative, and that natural numbers are closed under multiplication. In this case, addition as well. But that once we've got to that form of t, this was just the definition of an odd number applied for the product nm, so we can follow that bridge all the way back to the other side where we have now n and m must be odd. So that's what we were looking for. And again, that's just applying the definition of what it is to be odd. So that actually, once again, concludes another formalization. This proof here in structure is very similar to the last one, so I went a little bit quicker over it. But the goal of this video was to go through the process of taking an informal proof, one that we've maybe also constructed ourselves, and then try and formalize it by identifying the propositions, the underlying propositions in the way that they should be codified, and then also the rules of inference that we are applying as we go from one proposition to the next through our argument. Okay. These are probably the only formal proofs that we're going to take a look at in this series of videos. Again, because they tend to be tedious, and as our proofs get longer, the formal proofs get very, very long. And so what we're going to do in the next video and in the videos coming forward is focus more on informal proofs. And in the next video, I want to look at other kinds of proof other than the direct proofs that we've been focusing on in the last couple of videos. All right, that's all I have for this video, so thanks for watching, and we'll see you in the next video.